Thanks a lot. Yes, they are symplectic. So we'll see in a minute. Thank you so much for the invitation. I wish I could be there in person, but hopefully someday we'll be able to meet in person. Um, this is about joint work with Olga Plamenevskaya. And so yeah, everything is together with Olga. So the setup is familiar for this school at this point. We're going to be looking at
Recording in progress.
complex surface singularity, and this complex surface singularity. We'll have an isolated one. And so we can take an embedding in some affine space, take a ball around it, and look at its link. And so you guys have thought a lot maybe about these links. And so this is a three manifold. You can study its smooth topology and invariance, like this Heckard-Floer invariance. But for the purpose of this talk, I'm going to consider its geometry. So I want to look at the contact structure that's induced on the link of the singularity by the complex structure on the surface singularity. So we take the set of planes in this three manifold, which are invariant under multiplication by I, under the complex structure. And so I'll maybe refer to this link with the notation y(c). So y is a three manifold and c is the contact structure. So if you start with a singularity, you can of course consider its smoothings or Milner fibers. And that gets you from a singular complex surface to a smooth complex surface. And the important property is that the boundary three manifold doesn't change. And in fact, the manifold as a contact manifold with its contact structure also doesn't change up to contactomorphism. So one way to kind of generalize these smoothings, which have kind of nice complex structure, is to look at just any symplectic manifold which has that contact manifold as its boundary. So we can consider all symplectic fillings of this link. And so this is, I guess maybe the picture kind of looks the same in this very crude schematic, that we fix our boundary and we want a symplectic manifold which induces that contact manifold on the boundary. So instead of the inducing of the contact structure coming from looking at complex tangencies, here we maybe use a Liouville vector field that's transversely pointing outward to induce the contact structure, get a Liouville form. Alternatively, you could think of this much more analogously to the complex structure by choosing an almost complex structure, which is compatible with the symplectic form. There are notions of convexity that way. But I don't want to get too much into varying notions. In our case, pretty much every notion in the context we're working in of symplectic filling will be the same. Maybe the one technical caveat I should mention is, maybe I should put this adjective beforehand, is that I'll generally be considering minimal symplectic fillings, so not ones which have been blown up. Okay, so the main question that I want to consider is while these complex surfaces are examples of symplectic fillings, is there more to look at in the world of symplectic fillings than just the ones coming from these smooth deformations? So are there types of surface singularities where there are symplectic fillings that are not just Milner fibers, or maybe the resolution, the minimal good resolution. So these would be symplectic fillings, but they're ones that we already expect to have coming from the complex algebraic geometry. Does symplectic topology have more to offer? So that was the main question. And then so prior work kind of addressing this question looked at specific examples of types of singularities. And so a couple of papers of Ota and Ono first considered the simple singularities and simple elliptic singularities. And what they found in that case was that actually there aren't any interesting additional symplectic fillings. The only symplectic fillings of the links of these kinds of singularities are symplectically equivalent to the resolution. So I'm going to call a symplectic filling which is not equivalent to a Milner fiber resolution we're going to informally call these unexpected fillings. And so in this simple elliptic case, there were no unexpected fillings. Then you could look at cyclic singularities whose boundary is a lens space. And Liska had studied the symplectic fillings of lens spaces and given some kind of characterization of those symplectic fillings. And then Nemeti and Popescu-Pampu compared the symplectic fillings with Milner fibers for cyclic singularities and showed, again, there are no unexpected fillings showing up in that case either. So there's no unexpected fillings in these cases. And more generally, from cyclic singularities, you could look at quotient singularities. Bhupal and Ono had done some work to characterize properties of their symplectic fillings, and Park, Shin, and Urzua did the comparison with the Milner fibers to say, again, all of the symplectic fillings actually are showing up as Milner fibers or the resolution. So in all of those families, there were nothing was coming up in symplectic geometry that hadn't already come up in the complex deformation theory. By contrast, there are some examples of Akhmedov and Ozbachi where they looked at these kind of high genus examples, so not rational singularities, not elliptic. The minimal resolution was something like a higher genus curve with some particular normal bundle data. And in these cases, they found that there are infinitely many symplectic fillings with the property that the first Betti number is not 0. And if you're a Milner fiber, then the first Betti number has to be 0. And so none of these infinitely many could be a Milner fiber. And there's one that's the minimal resolution, and the rest were not. So this has infinitely many unexpected fillings. So you could ask, when should we really expect these unexpected fillings? What classes of singularities should we think these will have unexpected fillings versus they won't? So if you kind of look just based on the prior results, maybe a kind of first glance says like there's this difference between like rational singularities, elliptic singularities versus these kind of more higher genus general type kinds of singularities. And so maybe like rational singularities is a reasonable class to expect no unexpected fillings based on prior results. And there's a even simpler subset of rational singularities, which we looked at, which maybe is even more reasonable to expect that it has this behavior of no symplectic fillings beyond what's coming from complex deformation theory. So I want to talk about these rational singularities with reduced fundamental cycle. And so you guys discussed at the beginning of the week this Artin fundamental cycle. And in general, for a surface singularity, it has this form that it's some sum with positive coefficients of the components of the minimal good resolution, the irreducible components. And so we're going to look at ones where this fundamental cycle is reduced. And reduced just means that I don't have multiplicity for these divisors. So all of these coefficients are 1. Okay. So this is a condition that you can phrase in terms of this fundamental cycle, but it's easy to actually translate this if you can just see what the definition of this fundamental cycle is, to say what does that mean in terms of the minimal good resolution. So for one thing, we're only looking at rational singularities. So the minimal resolution graph is going to be a tree, and each of the irreducible components is going to be genus 0. And then the reduced fundamental cycle adds this extra condition on each vertex. So for each vertex, V, then I'm going to look at the number of edges adjacent to V. So if I focus on this one that I've highlighted in pink, it has 3 adjacent vertices, or sorry, 3 adjacent edges. So I've got valency 3, and then I'm going to look at that normal Euler number. So I'm just labeling these vertices with that normal Euler number because all the genuses are 0. So I've got 3 plus -5, so that's -2, and that is what I want to be a negative number. And I can look at each of the vertices here and one by one say, okay, this has valency 2 plus normal Euler number -2, that's 0. So yes, less than or equal to 0, that's okay. And I just go through, check that for all the vertices, And in this example, it's satisfied. So this is reduced fundamental cycle. Whereas this other example over here, if I just changed the normal Euler number of one of the vertices to -2, now I have still valency 3 there, but the normal Euler number is not sufficiently negative to be less than or equal to 0. So as soon as I have one vertex which doesn't satisfy this condition, this is not reduced fundamental cycle. Okay, so there's this kind of easy characterization in terms of the good resolution that you can just check. And so you could easily write down the resolution graph and say, this is an example of something with reduced fundamental cycle, or it's not. And yeah, so that maybe the other comment I wanted to make is this kind of situation where you have a vertex which fails this condition. Sometimes, especially in Hagar-Fleur, they like to call these bad vertices. And so a reduced fundamental cycle singularity has no bad vertices. If you want to compare with some of the classes that had been looked at earlier, reduced fundamental cycle includes all cyclic singularities. And it's a subset by definition of these rational singularities. And I'll use this RFC abbreviation for this class. Okay, are there any questions?
Question.
Okay, feel free to interrupt me anytime if questions do come up. All right, so the other aspect of these reduced fundamental cycle singularities that's really nice looking from the symplectic geometry perspective is that they're also kind of simple from the contact geometry, symplectic geometry point of view. So there's a theorem of Gagini-Gola and Plemnitskaya, which says that these RFC singularities are exactly the ones whose link, so the link of this singularity has what's called a planar open book decomposition. So I'm hoping that you discuss open book decompositions and leftist fibrations a little bit in Elsa's class. I only saw Monday videos. I'm not up to date. But we have, a correspondence between contact structures and open book decompositions, where an open book decomposition is a fibration of my 3-manifold in the complement of a link called the binding. So B is a link in Y, like a knot or a link, that kind of one-dimensional submanifold. And in the complement of that link, it should be fibered over the circle. And to say that it's a planar open book means that the fibers of that fibration are genus 0. And so with open book decompositions, the genus of the fiber could be anything. And there's this stabilization operation, which can change the open book decomposition, but keep the contact manifold that it corresponds to the same. And in general, that stabilization operation can increase the genus of the fiber. And so one kind kind of invariant that's interesting to contact geometers is the minimal possible genus of any open book decomposition which is compatible with a contact manifold. So for these links of singularities, those contact manifolds, they only have a genus 0 open book decomposition if they're in this RFC class. And so that's a kind of nice property of this class of singularities. And
so there's a question. So I just forgot. RFC is what? Can you is this on? So for instance, AN is RFC.
Yes, AN is RFC. Any cyclic is RFC.
So if I take a trefoil knot on S3, this means that there is open book decomposition with genus 0 fiber. Yes.
So for the trefoil in S3, you can consider the fibration because the trefoil is fibered. So that will be a genus 1 fibration.
Yeah.
So that's one open book decomposition on S3. And that, but there's another open book decomposition on S3, which is just the binding is the unknot, and there's a disk filling the unknot, and I can fiber the complement of the unknot just by disks, and that's a genus 0 one. And so I can relate those both are compatible with the tight contact structure on S3. And so there's a set of sequence of stabilizations that will relate my genus 0 open book decomposition for S3 to that genus 1 open book decomposition for S3. So genus 0 planar open book means there exists a genus 0 open book decomposition, not that every open book decomposition.
So there exists a genus 0 open book decomposition of the trefoil knot in S3 in particular. This theory says.
Well, there exists a genus 0 open book decomposition for S3 with a standard tight contact structure.
Okay, okay. Thank you.
So the binding might change. So the trefoil or the unknot, like that is part of the data of the open book decomposition. Any more clarification or questions I can answer? So I think maybe the advantage that I want to
Excuse me, I have a question. When you say symplectic feelings, you mean always minimal symplectic feelings?
Yeah, I always mean minimal.
Okay, thank you.
Yeah, because yeah, this okay. So in particular, in this next theorem of Wendell, this is the symplectic thing that's good about contact manifolds with planar open book decompositions, which is that their minimal symplectic fillings are all, so one way to say this is, if I have a planar open book decomposition that has some monodromy, so this S1 fibration, and go around the S1, that gives me a monodromy of how do I get from a fiber to itself going around the S1 ones. So that's a diffeomorphism from the fiber to itself. And so that's this monodromy phi. And so what Wendell proved is that for every minimal symplectic filling is in correspondence with a factorization of that particular monodromy, that particular diffeomorphism, to write it as a product of positive Dane twists. And another way to think about this is every minimal symplectic filling of the planar contact manifold has a planar Lefschetz vibration whose boundary is that particular open book. So like with S3, I had lots of different open books, maybe of different genus, maybe some of the same genus, but the advantage that you get with planar open book decompositions is in order to study the contact manifold itself, I don't need to look at all possible open book decompositions that are compatible with that contact manifold. I just get to look at one planar one, and every single symplectic filling is going to have this Lefschetz vibration structure whose boundary, so it's going to be a Lefschetz vibration over the disk. So around the boundary of the disk, that circle, then that's going to give my open book decomposition vibration. So that is a way in which symplectic fillings get kind of reduced to this mapping class problem where we're looking at a particular diffeomorphism, a particular mapping class element of a surface, a genus 0 surface with some boundary components, and trying to write it in different ways as positive products of positive Dane twists. So this gives some limitations in this class of planar contact manifolds on the symplectic fillings. It makes the problem a bit more combinatorial and accessible. And so that's maybe some indication about whether there may or may not be some unexpected fillings. So it's maybe leaning towards this is a more limited context for symplectic fillings.
Is it the case that these planar open book decompositions can be understood by the sandwich presentation of the singularity?
Yes, absolutely. So this class of singularities, reduced fundamental cycle, are exactly a subset of sandwich singularities. And that's actually going to be really important for us later on, because we're going to use results of Jeong and Van Straten, which analyze these sandwich singularities, but we're going to just restrict to this subclass of the reduced fundamental cycle one. So all of these planar open book ones are sandwich singularities. Okay, so this is the class we looked at, and we tried to study their symplectic fillings. And what we found is, despite the fact that this is a nice, simple set of rational surface singularities, despite the fact that their symplectic fillings are somewhat limited because of this planarity condition, there are still unexpected fillings showing up within this particular class of singularities. And more precisely, if you give me any positive number, I can find a singularity in this nice planar reduced fundamental cycle class where I have at least that many symplectic fillings, the number you gave me, such that none of them are Milner fibers. So now I'm going to be a little bit more precise about what I mean by they're not a Milner fiber. Like what does is mean? And it is a Milner fiber. So the equivalence I'm using is they're sufficiently different that even their diffeomorphism type relative to some boundary data, essentially, which is the open book decomposition, that they're not diffeomorphic rel boundary to a Milner fiber. So I've got these kind of significant differences between the symplectic fillings that we're finding and the actual Milner fibers. And I'm not separating out the resolutions as a different case anymore, because for this class of singularities, the minimal resolution is diffeomorphic and symplectic deformation equivalent to example of a smoothing or this kind of Milner fiber smoothing called the Artin component. So it's the smoothing in the Artin component. So, okay, this was one of our main results. And you could ask, okay, there exist some of these singularities in this class with unexpected fillings. How common within this class are singularities with unexpected fillings? So the first example that we have in terms of its resolution graph, where there's an unexpected filling, is this graph. So I've got one vertex with normal Euler number -11, and the rest are labeled with -2s. And I've got a bunch of arms, so there are 10 arms coming out, and I've got to have like these chains of -2 spheres sufficiently long coming out from this central vertex. So this was the first example, but what we can show is if you find this example as a subgraph of any other example, so maybe I can extend this to some other singularity with reduced fundamental cycle, then this new graph still has unexpected fillings. And so that this first one, I can say there's at least one unexpected filling. For our result to get at least n symplectic fillings, it's kind of a similar picture, but there are more arms and they're longer, and this coefficient on the central vertex becomes more negative with more arms. So there are lots and lots of examples because I could extend any of these graphs with unexpected fillings however I want in this RF, satisfying this condition on the valency of the vertices, no bad vertices, and get another set of examples with unexpected fillings. So there's like a huge class of graphs that I could draw where these unexpected fillings show up. But there are also plenty of singularities in this class which do not have unexpected fillings. So we'd seen some of those examples, the cyclic singularities, is AN, the simple singularities, but more generally, we could show that if you've got all of your normal Euler numbers being sufficiently negative, less than or equal to -5, then there are no unexpected fillings because actually there's only one symplectic filling, and that's the one that looks like the resolution or this Artin smoothing. So in our examples, we kind of needed these large number of chains of -2 spheres. If we don't have any -2 spheres and kind of a little bit stronger, all of the numbers decorating these are at most -5, then there's just nothing interesting in terms of the symplectic fillings. So there's some space in between to explore. In some ad hoc examples, we can say whether or not there are unexpected fillings, but we don't have a general characterization of which singularities in this class do or do not have unexpected fillings. Any questions about the statements of the theorems?
If I remember well, if all the self-intersections are smaller than -5, there is also just one smoothing, right?
Yeah, exactly. And so this was proven, so in the smoothing case, this was proven by Jung and van Straten. And so we kind of extended this to the symplectic case. And this was a part of a conjecture of Kolar, just applied in this reduced fundamental cycle case. But there's a kind of more general conjecture of when there's a unique smoothing. And yeah, you could kind of generalize that to there's a unique symplectic filling. Okay, so let me say kind of the main input that goes into the proof. So this is proving a theorem by proving another theorem. But here's the idea. The first thing that we need to do to be able to compare symplectic fillings and Milner fibers is to understand something about the Milner fibers. So I actually didn't state this in the theorem here, but in our examples, we can make all of these symplectic fillings, we can make them simply connected, if you like. And so in particular, first Betti number is 0. So this method that Akhmedov and Osbachi used to say that there are examples of symplectic fillings which are not Milner fibers by using the first Betti number to distinguish them, that doesn't apply in our case. So we're going to distinguish them from Milner fibers in a kind of more direct way, which is to first understand some results of Jung and van Straten, which gave a way to understand Milner fibers for these reduced fundamental cycle singularities, and actually more generally sandwich singularities. So the reduced fundamental cycle case has some kind of nicer properties than the general sandwiched case, but their results that I've kind of stated here apply generally to sandwich singularities. So they gave a correspondence between the smoothings of the surface singularity, the sandwiched surface singularity, with complex deformations satisfying certain properties of a complex plane curve singularity with some decorations that they associate to that particular singularity, the surface singularity. So you start with a surface singularity, and basically they get this kind of much simpler deformation theory problem to study by taking it from a surface singularity to a plane curve singularity. So the dimension has gone down from surface to curve, and we get to just study things in the complex plane in C2. And so that deformation theory is much easier to understand. And so that makes it much more manageable to study the deformation theory of these sandwiched or specifically reduced fundamental cycle singularities. And so what we did with Olga is to get a similar type of correspondence for symplectic fillings. So instead of just looking at the smoothings, the deformations, we proved an analogous theorem for symplectic fillings that they are also in one-to-one correspondence with a kind of deformed version of these decorated plane curves that de Jong and Van Straten associate to the surface singularity. And so the kind of main difference between the deformations and the fillings, symplectic fillings, is that is coming from the differences between complex deformations versus what we're calling graphical homotopies of these plane curves, singular plane curves. So if I want to find unexpected fillings, I want to find differences between these kinds of deformations. So let me kind of give you an idea of what graphical homotopy means for these plane curves just by showing an example. So this is my plane curve singularity. At this point, I've got just a bunch of, like linear pieces intersecting transversely, all at the same point. And if I do a complex deformation, I can separate out these intersections in different ways, but there are some limitations on what I can get from a complex deformation. With a graphical homotopy, I'm going to allow myself to just push these components, different irreducible components, around smoothly, and I don't need them to immediately fall into the final position, but eventually I can get them to intersect according to this sort of picture. And so this is a new curve configuration, and it kind of differs from what you would see in a complex deformation, because if you focus on this red curve, a kind of classical projective geometry theorem says that if I have the black lines arranged as they are, going through these points, little ABC and big ABC as follows, then the 3 points here, here, and here are automatically going to fall into a line. They're automatically collinear. And so any complex line arrangement would have to, where a line passes through 2 of these points, would have to pass through the third, like this kind of dotted green line. And so instead, we're going to have it miss that 3rd point and intersect at a different place along the 2 lines that intersect there. And so that's in itself not exactly a proof that it's not related by a complex deformation, because actually we can do analytic deformations, but we're able to show that this arrangement, once we've kind of pinned down one of those intersection points with an extra line, is not obtainable from a complex deformation from this original singularity, plane curve singularity. And by contrast, it is perfectly obtainable from this arrangement using a graphical homotopy, which is more flexible. So this is maybe our first example where we get an unexpected filling that comes from this curve arrangement that I can get from a graphical homotopy, but not from a complex deformation. Any questions? I think I see a hand in the audience. Okay, so I'll wait.
The stuff about the not being a complex deformation, that's from your paper from a couple of years ago? Generalizing that?
Well, so this is a specific argument in the paper with Olga. So yeah, I do have some earlier work about when you can actually find a line arrangement with in CP2 in the complex projective plane, which is symplectic or exists topologically compared to the complex setting. And this is actually a bit more subtle because we're in the open setting in C2. And so things are analytic instead, like you can use analytic equations to describe these things. And so we have to like allow for higher order terms that are not just linear to rule out the complex deformations. And so what it kind of comes down to is we do this sort of like zoom in blow up where we sort of write out, assuming we've got this maybe higher order terms, but if the deformation is analytic, as we kind of shrink it, trying to reverse the deformation back from this big configuration back to the original singularity, if that deformation existed, then we would end up with an actual complex line arrangement. Like it would imply the existence of a complex line arrangement, which satisfies the incidences of this configuration, possibly with some incidences degenerating down further. So some points might start to coincide, but we can rule out the possibility that some of the points coincide with the fact that the lines are different from each other. And so like the only degeneration of this is down to the actual pencil itself. And so that's kind of what goes into the proof, but it is a little bit of a subtle argument.
That sounds cool. Thanks.
Yeah, good. Okay. So maybe just like to give you an idea of where does the plane curve singularity come from the surface singularity or from its resolution graph. I have a couple of examples. So this is Jang and Van Straten's strategy, and it tells me how do I get from my surface singularity or its resolution graph to a plane curve singularity, and it's going to be decorated by some weights, some positive integer weights. So the process is I want to think of these RFC singularities as sandwiched. So what I'm going to do is embed that minimal resolution into a blow up of the complex plane. And the way I do that is I take that resolution configuration. In this case, there's a -6 curve and 4 -2 curves. And I'm going to add on additional exceptional divisors, -1 curves. So the red ones are like actual curves I'm adding on. The green are these kind of reference disks that I'm going to keep track of. So green arrow represents a small disk, which is transverse to the red genus 0 curve that I've added on. And I want to add on these -1 curves in a way such that the whole graph will blow down to nothing. And so with these reduced fundamental cycle singularities, you can actually do this in a relatively systematic way. There's a bit of a choice, but I want to make sure that that inequality about the valence and the normal Euler number is actually equality at all of the vertices except after I add on these -1 curves. It should be equality everywhere except at one vertex. In this case, it's the central -6 one where the inequality is off by 1. And so then if I do that, you can see as I go from this picture to the next one, I'm going to start blowing things up, blowing things down. I blow down all the red curves, and now I've got some new -1 curves, and I'll blow those down. And then I have a new -1 curve, and I blow down that final -1 curve, and that gets me to this configuration. So these little green arrows represent disks, and as I do the blowdown, I'm gonna see where do they go under that blowdown, and at the end they all intersect transversely at a point because I blew down an exceptional divisor that intersected them all at distinct points. In another example, if I start with this -2, -3, I can add 2 exceptional -1 curves like this with their little transverse disks. I start blowing down the red curves. I get a new -1 curve to blow down. And when I blow that one down, it brings these 2 green arrows to intersect transversely at one point on the final divisor curve. And so when I blow down that curve, that turns that transverse intersection into a tangency. So this is my plane curve singularity. In this case, it's 2 components intersecting tangentially. And then these decorations are basically keeping track of how many blowdowns what was the arrow involved in. So each time I do a blowdown that intersects the arrow, I increase my decoration by 1. So like for this arrow, I did 1 blowdown, so that got it to 1. I did another blowdown of this -1 curve, got it to 2. And then my last blowdown, which affects it, brings it to a 3. Whereas for this arrow in the middle, I blow it down once. And then at this step, it's not involved in any of the blowdowns. So that stays as a 1. And then it gets an extra blowdown to bring its decoration up to 2. So that's the thing that I associate to my surface singularity. And if I have a sandwich singularity more generally, I can find such a decorated plane curve singularity. But the RFC ones have this property that there always exists such a plane curve singularity where all of the irreducible components are smooth. So that's what's a little bit nicer about these ones. So each component is smooth, but they intersect to give a singularity. Okay, and then so for the deformations, whether it's a complex deformation or our graphical homotopies, at the end, you need to have this property. So de Jong and Van Straten, these are kind of their conditions to say, this is when you actually get a smoothing. If you have a complex deformation of this plane curve singularity, where at the end, all the singularities are transverse, they could be multi-points of multiple components intersecting all at the same point, like in this picture. And then the weights, these numbers, that tells you the number of marked points. that I have to have on each component. And the rule is each of the transverse intersections has to be a marked point. So I can have additional marked points, but at least I have to mark every transverse intersection. So basically these weights put a limit on the number of transverse intersections you can have. So here we had initially a tangency, so we had to deform to get rid of that tangency and turn it into transverse intersections. In the other example, everything was already transverse to begin with, and so we could kind of do a somewhat trivial deformation, but just spread out the marked points. So one of them has to be this transverse intersection, and then there are extra markings to add up to the right weights. Another option is to do a deformation which spreads out the lines. And this actually is a complex deformation. I can just rescale the linear equations that describe this straight complex line arrangement to get it down to the pencil. And this satisfies the weight constraints. There's one of these components with only 2 marked points, and the others have 3 marked points. And that's aligning with what we had. One thing that you couldn't do is get a kind of generic line arrangement. So that's a perfectly good deformation, complex deformation of this singularity, but it doesn't satisfy the weight constraints because, for example, this component would need to have 4 marked points, and that's too much. I should only have 3 marked points on each component at the most. Maybe I'll just quickly say is some differences between complex deformations and graphical homotopies. The complex deformations obviously have to be complex analytic, whereas graphical homotopies, these just have to be smooth. But what seems to actually be more important is that the complex deformations are sort of immediate changes. You go from the original curve singularity immediately to the new configuration, whereas with graphical homotopies, we can have a different intermediate stages before we reach the final configuration. And so to get a symplectic filling, we don't necessarily have a deformation that goes from the singular object to the filling. We just have the filling might be kind of unrelated from a deformation theory perspective to the singularity. It just has to have the same contact boundary. So we have more details in the paper in the last section about exactly what is and isn't the sort of key important difference between complex deformations and graphical homotopies, but it's boring unless you have thought about this too much. So I won't get into it here. So maybe just the final piece of information is like how do we prove this correspondence between symplectic fillings and these graphically homotoped curves? So in Guillaume van Straten, they're really using algebraic geometry and the full power that you get from the complex equations that describe the smoothings. Whereas we have a very different set of tools available in the symplectic setting. But so the one direction to get from a graphically homotoped curve to a symplectic filling, the way that we see a symplectic filling is using the Lefschetz vibration. So the picture I start with my curves in C2, and I'm just going to look at the projection map from C2 to C. And in the complement of these curves, a generic fiber is just going to look like a plane with some holes cut out where I deleted the curves. But then whenever I get one of these transverse intersections, some of those holes are going to smoosh together. And so it's not quite a fibration because the fiber is changing. I've got 3 holes here and only 2 holes here. So this is a kind of bad singular fiber. And to make the singular fibers maybe still singular, but a little bit better, I'm going to blow up at each of those marked points. And that's going to change.
You just have very few minutes left.
Yes, I know.
So let's say the 0 equals 3 or something like that.
Okay, I will do, yeah, one more minute. So let me just draw what the singular fiber turns into after the blow up, which is I get this new exceptional divisor included in my fiber, and my holes, so I think this is the one where I blew up here, so this was just a single hole. They now get separated out because they were transverse, so they get separated in the blow up into 3 holes in this exceptional part of the fiber. And if I look at the equations, the singularity that's left over is this place where the exceptional divisor intersects the proper transform of the fiber. And this is exactly a Lefschetz singularity. So my standard projection from C2 to C in the complement of the curves becomes a Lefschetz fibration after I blow up and take the complement of the proper transform of the curves. And that Lefschetz vibration is the symplectic filling that I'm looking for associated to these graphically homotoped curves. And what we check is that the open book decomposition doesn't depend on which graphical homotopy we had. And so it agrees with the ones coming from the, say, the Argent smoothing, which gives us the actual open book decomposition for the contact manifold, which is the link of the singularity that we wanted. And in the opposite direction, we're using this Wendell result that in fact every symplectic filling has a planar Lefschetz vibration, and we reverse engineer the curve configuration that we want using the data of the Lefschetz vibration. So we kind of push this in both directions to get this correspondence in the symplectic setting. All right, so I'm sorry for going over time, and that's all I want to say. I'm open to any questions, but thank you so much for having me here.
Some questions? Yeah.
I would like to know whether you have other examples outside these RFC singularities with these unexpected symplectic fillings.
So this is a very interesting question, and we've tried to maybe get more general towards the sandwich singularities. One subtlety that makes it really complicated is that from the symplectic filling perspective, I don't really see from the link of the singularity, just from its contact geometry, what analytic type the singularity is that fills it. And so when we're saying these symplectic fillings are not agreeing with any Milner fiber, what it really means is it doesn't agree with any Milner fiber of any singularity which may be analytically different, but is topologically the same as the singularity we started with. So for these reduced fundamental cycle singularities, that's kind of more manageable to deal with. And they're, like, more generally, there are some singularities which I think the right terminology is pseudo-taught, that there's some control over the different analytic types which are in the same topological type. But I think it's a pretty limited class of singularities that satisfy that property. And so I think more generally, it's just hard to say enough about the smoothings, the Milner fibers, to distinguish a symplectic filling from any possible Milner fiber, unless we use something like this Akhmedov-Osbachi with the first Betti number. But yeah, so it's actually quite open for more general, but we've tried to think about some other classes of singularities, and that's one of the problems that we got stuck with. The other problem for more general sandwich singularities is we don't have these planar open books. So we might be able to produce examples of symplectic fillings, but we won't have a very complete understanding of what all the symplectic fillings are. But yeah, there's lots of interesting stuff to do. Sorry.
Okay. Actually, I have a comment about these singularities, which are called minimal, these special rational singularities, which are called minimal by Kolar or Spivakowski. Actually, they have a very special properties. They have a metric property. They are Lipschitz normally embedded, which means that their inner and outer metric are by Lipschitz equivalent. And actually, they are the single one among rational singularities which have this property. And maybe, and there are other classes of singularities which have this LNE property, very rare, but maybe it is a way maybe to find some other classes in your case. I don't know. So it's just a comment.
That's a good idea. Yeah, I'd be interested to talk more about that. Yeah.
So I remember that there was a way to decode this combinatorial problem of putting the points on the branches of the curve, and then we used these matrices with zeros and ones, just incidence matrices. So is it true that also in your case each of these things is given by such an incidence matrix, or can you realize all the incidence matrices, or are there conditions?
Yeah, so there definitely is an incidence matrix of kind of points and lines. And in general, it seems to be a very difficult problem of which incidences can be realized. So if you can draw it, let's see. Actually,
can you do it with your pseudo lines, or did these homotopy?
Yeah, so if you can draw it, so okay, definitely if you can draw it in the real plane, then it will be possible to realize it from this graphical homotopy. More generally, you can not just have it as a drawing in the real plane, but you can add some braiding between the strands, and that will give you more freedom with the incidences. And if you have any kind of this sort of like braided wiring diagram,